Hi. Welcome to Linear Classifiers in Python. In this course you'll learn all about using linear classifiers, specifically logistic regression and support vector machines, with scikit-learn. Once you've learned how to apply these methods, you'll dive into the ideas behind them and find out what really makes them tick. At the end of this course you'll know how to train, test, and tune these linear classifiers in Python. You'll also have a conceptual foundation for understanding many other machine learning algorithms. This course consists of 4 chapters, which are applying logistic regression and SVM, loss functions, logistic regression and support vector machines. In this video, you will learn the basics of applying logistic regression and support vector machines, SVMs, to classification problems. You'll use the scikit-learn library to fit classification models to real data. Let's begin with scikit-learn refresher. In this course we'll assume you've taken the prerequisite courses or have a similar level of knowledge. In this video we'll briefly review the standard syntax of the popular machine learning package scikit-learn, which was covered in the prerequisite course on supervised learning. We'll continue to use scikit-learn extensively in this course. To remind you, supervised learning refers to learning a relationship from examples of input-output pairs, usually called X and Y. There are a few typical steps of supervised learning. First, let's load the newsgroup's data from scikit-learn's repository of built-in datasets. We can inspect the shape of X and Y and see that we have about 11,000 training examples, each with about 130,000 features. In this case the features are derived from the words appearing in each news article, and the Y values are the article topics, which is what we're trying to predict. Next, we can import the k-nearest neighbors classifier, or KNN for short. We instantiate the classifier, and store it in the variable KNN. This is the step where we specify model hyperparameters, like the number of neighbors for KNN. Next, we can fit the model using the fit method. This is standard syntax across all of scikit-learn. Then, we can make predictions on any dataset, including the original training set X. The variable y_pred now contains one entry per row of X with the prediction from the trained classifier. Let's evaluate our KNN classifier. We can use the score function to compute the score on the training data, and it's tempting to be satisfied by almost 100% accuracy. But this number isn't particularly meaningful, since we want to know how the model generalizes to unseen data. This ability to generalize is often measured with a validation set. Scikit-learn provides a convenient function to split up our data. Train_test_split. X_train and Y_train now contain the training set, and X_test and Y_test now contain the test or validation set, which by default contains 25% of the examples. Before we compute the score on the test set, we need to make sure our model is training on the training set only, otherwise it would have access to the test set, defeating its purpose. So we refit on the training set, and compute the test score. We see that we have a much lower testing accuracy. Whether or not 66% accuracy is considered good depends on the situation, but the training error was definitely a poor representation of the model's ability to classify new data. In this video, we'll see how to run logistic regression and SVM with scikit-learn. The logistic regression class in scikit-learn is used just like the other models you've seen in the prerequisite course. First, we import logistic regression from scikit-learn. You'll notice we're importing from linear_model, because logistic regression is a linear classifier. More on this later. Then, we instantiate an instance of the classifier. We fit the classifier on our training set, and then we can predict, compute the score. Let's try this on an example dataset, in this case the wine classification dataset built into scikit-learn. We load the dataset. Then, we create and fit a logistic regression object. We compute the training accuracy and see it's about 97%. Scikit-learn's logistic regression can also output confidence scores rather than hard or definite predictions. Let's do this with the predict_proba function and test it out on the first training example. Here the classifier is reporting over 99% confidence for the first class, and very low probabilities for the other two. As a reminder, the little e means 10 to the power of, so you should interpret that first probability as 9.9 times 10 to the power of -1, or 0.99, or 99%. We'll discuss these probabilities more in Chapter 3. In scikit-learn, the basic SVM classifier is called linear SVC for linear support vector classifier. The linear SVC object works exactly the same way as logistic regression. Note that this data set has more than 2 classes. Scikit-learn's logistic regression and SVM implementations handle this automatically. We'll talk about how this works in Chapter 3. We can repeat these steps again for the SVC class, which fits a nonlinear SVM by default. With default hyperparameters the accuracy is not particularly high, but it's possible to tune the hyperparameters of this nonlinear model to achieve 100% training accuracy. Such a classifier could be overfitting, which is a risk we take when using more complex models like nonlinear SVMs. Later in this chapter, we'll discuss what it means for a classifier to be linear or not. By the way, So far we've used the default hyperparameters for logistic regression, linear SVC, and SVC. To remind you, a hyperparameter is a choice about the model you make before fitting to the data, and often controls the complexity of the model. If the model is too simple, it may be unable to capture the patterns in the data, leading to low training accuracy. This is called underfitting. On the other hand, if the model is too complex, it may learn the peculiarities of your particular training set, leading to lower test accuracy. This is called overfitting. This is a fundamental trade-off in machine learning. In chapters 3 and 4 we'll delve into these classifiers in more detail so that, by the end of the course, you'll understand what many of the hyperparameters represent, how they affect this fundamental trade-off, and how to go about setting them. In this part of the video, we'll discuss what it means for a classifier to be linear. A decision boundary tells us what class our classifier will predict for any value of x. In this image, the classifier predicts the blue class in the blue shaded area, where feature 2 is small, and the red class in the red shaded area, where feature 2 is large. The dividing line between the two regions is called the decision boundary. This decision boundary is considered linear because it looks like a line. The line doesn't have to be horizontal. It could be in any orientation. This definition extends to more than 2 features as well. With 5 features, the space of possible x values is 5-dimensional, which is hard for me to draw on a slide. In that case, the boundary would be a higher dimensional hyperplane cutting the space into 2 halves. A nonlinear boundary is any other type of boundary. Sometimes this leads to non-contiguous regions of a certain prediction, like in the figure. In their basic forms, logistic regression and SVMs are linear classifiers, which means they learn linear decision boundaries. In chapter 4 we'll discuss nonlinear versions that produce boundaries like the one on the right. Here's a list of some important vocabulary we'll be using in the course. Classification is supervised learning when the y values are categories. This is in contrast with regression, where we're trying to predict a continuous value. We've defined decision boundaries and linear classifiers on the previous slide. A dataset is called linearly separable if it can be perfectly explained by a linear classifier. Here's an example of a dataset that is linearly separable and one that is not. In the left figure, there's no single line that separates the red and blue examples. Note that for now we're just talking about binary, or 2-class, classification. Later in the course we'll discuss multi-class classification, with 3 or more categories. On the other hand, in the right-hand figure we could divide the 2 classes with a straight line, so it's called linearly separable. Thanks for watching. In the next video of the playlist, we will discover the conceptual framework behind logistic regression and SVMs. This will let you delve deeper into the inner workings of these models. Please feel free to ask any questions in the comments section. Like and subscribe to stay updated about our upcoming videos about artificial intelligence. See you in the next video.